Hey everyone, so today we're going to work on how to cover Riemann sums using the tables, and eventually we're going to make a video on using the trapezoidal rule as well. So I'm just going to cover, if you have access to this worksheet, I'm just going to cover the first problem, make a few videos on that, and then you should be able to figure out the rest. So let's get started. So focusing on 1a, we're given a table where we're not given an explicit function, but we are given the t values and its associated y values, or f of t values. And part A is asking us to estimate the integral from 0 to 120 of f of t by using the left Riemann sum with 6 subintervals. So something I want to emphasize is that when they give us this term subintervals, it's pretty much equivalent to the number of rectangles that we're going to be drawing, as Riemann sum focuses on using rectangles to help us approximate our area under the curve. So what I'm going to do, I'm just going to sketch it out for visualization purposes, because the integration part of calculus is very geometrically heavy, and it's kind of good to be able to model what is happening in the problem. So I know I'm going from 0 to 120, so I'm just going to sketch that out. And what I'm noticing is that as my x values increases, my y values increases. So I'm just going to, let's see, at 0 to 1.2, I'm just going to do something like this. Whether the function is actually curving or not, I do not know, but I'm just going to put it in there just as a habit. Okay, so this is my boundary from 0 to 120, and since I'm using the left Riemann sum, I'm going to be making integrals where the left side of the rectangle is touching the curve. So before I even do that, my 6 subintervals by default in the Riemann sum is going to be equally spaced, because I have no other way of, I don't want to overcomplicate my setup. Plus my t values are equally spaced anyway, so I want to just go, I just want to use that logic by default unless I'm given something else. So with that being said, I want to make sure what the width of the rectangles are. Now, you can pretty much take a guess that they are going up by 20 because of just how they're skip counting. But if you forgot how to find the width of the subinterval in general, you would use the formula b minus a over n, where b minus a are the upper and lower limits of the integral. So in this case, a is the 0 and b is the 120, and n represents the number of subintervals or rectangles you want spread throughout the area of your graph. So I'll be doing 120 minus 0 over 6, which would just give me a width of 20. So that means from 0, I'm going to skip count by 20 all the way up to 120. So 20, 40, 60, 80, 100, and 20. So now I'm going to start generating my left Riemann rectangles in this problem. And what I'm going to do, I'm going to first kind of highlight what the total area is here. I just want to add some color to it. And then I'll show you that when you do your rectangles of the left Riemann sum for this diagram, we can discuss whether it's an overestimation or an underestimation as well, just to throw in some additional concepts in there. So okay, let's start with the first left Riemann sum. So I'm going to start with the left side of my rectangle, because my rectangle will be between 0 to 20, and my left side of the rectangle is hitting the curve. And I just carry this over and drop it. So what I like doing at the same time is building up my formula. So since the idea of the left Riemann sum estimation is to pretty much add the total areas that you're dealing with, I'm going to write a sub t as area total equals, and then I'm going to just add all the areas of the individual rectangles. So this is my first rectangle. Now, since the area of a rectangle is length times width, I am taking the height of the rectangle as its length and the width as its actual width. In this case, it should be 20 for all rectangles. So I know I'm going to be multiplying by 20 for every rectangle I have. So with that being said, I'm going to identify what the height of this rectangle is. And since the left side of the rectangle is touching the curve, that will technically be f of 0 times the width of the rectangle, which is 20. And then I keep up with the same pattern. So I'm going to start from 20, go up to the curve, draw it over. My height is f of 20 times 20, which is the width. And then I just keep going on with this pattern. So I have f of 40 here. So f of 40 times 20 plus I have f of 60 here. So f of 60 times 20. I have f of 80 here. So f of 80 times 20. And then I have f of 100 here. So plus f of 100 times 20. Sorry. And I do clearly have 6 rectangles, which represents my 6 subintervals, so I've done this correctly. What I want you to notice is that all of the terms are being multiplied by a width of 120, so I can rewrite this as 20 times, and I'm pretty much factoring out everything that I multiplied with. And this will be much easier if you have to evaluate this by hand. Instead of like distributing everything, you can just focus on combining the values before you multiply by your width or whatever that is. So if we start substituting, we have 20 times f of 0. Now I'm going to start referencing the table. F of 0 is 1.2 plus f of 20 is 2.8, f of 40 is 4, f of 60 is 4.7, f of 80 is 5.1, and f of 100 is 5.2. You add this all up and multiply by 20, you should get an approximation. I'm going to actually use the approximation symbol. Sorry, correct yourself on that because this is an approximate Riemann sum. I'm going to use the approximation symbol, and I get 460. And that will be it for part A using the left Riemann sum. So if you have any questions or comments, please leave them in the comment section below, like and subscribe, and I'll be making another video for part B, C, and D. Bye!